Good afternoon, everybody. It is my pleasure to introduce to you Dr. Trifon Trifonov from Heidelberg University, precisely the Landessternwarte up the Königsstuhl. Trifon received his PhD under the guidance of Andreas Quirnbach in 2014 with a thesis dealing with multiple planetary systems around giant stars, combining high precision radial velocity and dynamical modeling. After having received his PhD, Trifon moved on to Hong Kong, where he spent 2.5 years. Afterwards, returning to Heidelberg again, was a postdoc at the MPIA between 2016 and 2024, and since then is back at the Landessternwarte in the instrumentation group as scientist. I don't want to give too many details, but besides being an author of Nature and Science papers, Trifon received in 2020 the prize, the Young Scientist Prize in Physics from the Göttingen Academy of Science and Humanities. He is currently involved in a ExoRestart project. This is one of project funded by the Bulgarian Science Foundation. It is also known in the field for his nice piece of software, the ExoStriker, for orbital modeling of planetary systems. And perhaps not too big a surprise that today's topic goes along these lines. And he's presenting something on strongly acting multiple planetary systems as a Rosetta Stone for planet formation.
Yeah.
Trifon, welcome.
Thank you.
And take it away.
Thank you very much. First, I would like to thank the organizers for the kind invitation. It's a real pleasure to be here and to be able to tell you a little bit about my favorite topic, multiplanetary systems, and in particular those composed of gas giants. And I would try to convince you why these are very important for the planet formation theories, because we have more anchors there where we can constrain how planets actually form and migrate. I know I've been told that I have to prepare several slides just as an introductory, just to be on the same page, because I know that there are many young bachelor and master and PhD students. So I'm pretty sure everybody knows how planets have been discovered. But anyway, it's nice to make one very short introduction. Today I will talk about two methods, the two most prominent methods. That's namely the radial velocity method, or the Doppler method for detecting exoplanets, and the transit method. So in case of the radial velocity Doppler method, we know how that goes. This is indirect method for detecting exoplanets. So we obtain high precision stellar spectra and track for temporal variations in the stellar absorption lines. And as we know, if the lines are blue shifted, then the star comes towards us, and when it's red shifted, it goes away. And we can obtain many spectra over the many different epochs, and we can reconstruct those so-called radial velocity curves. And the radial velocity curve is very characteristic for the orbital geometry and eccentricity, and therefore we can, in principle, obtain important piece of information such as eccentricity, minimum mass, and other properties such as the geometry, how it's actually aligned with respect to us. Now, for multiplanetary systems, it's just the observatory curve as a sum of the Doppler signals induced by the all orbiting bodies in the system. As you can see here, I hope you can see it well. I'll just move with my mouse. So the result at the radial velocity curve is just the composition of the individual Keplerians of the planets. Of course, as you will see today, it's more complex than that. Okay, but just as a first approximation, think that it's not so complicated to detect multiplanetary systems in a way, because it's easy to decompose these signals. Now, the radial velocity Doppler, I was teaching this afternoon, exactly these slides. It's the best method to detect and to constrain the eccentricity of exoplanets. Okay, so we can get from the specific shape of the radial velocities, we can get the geometry, how it's aligned, the eccentricity, the phase, orbital period, of course, and the semi-amplitude, which we can after that convert to minimum mass. And minimum mass, because the only problem with the radial velocity method is that we cannot get orbital inclination, at least not easily, just by taking a spectra, because what we measure is only the red vector over here. This is the radial component of the movement of the star with respect to the common mass center. So in principle, it is possible that instead of planet, that we could in principle observe, let's say, brown dwarf, or in very, very rare cases, a low mass star. I'm just trying to emphasize very rare cases. So we know that if you take all possible orientations of the orbits, it's most likely to observe actually near the minimum mass. And so basically, we don't know whether the star moves in this plane or in this plane, but it's more likely that it's nearly edge-on. So we're pretty safe in terms of statistical sense that we detect a large number of exoplanets with the Doppler method. Now, for the transit method, we obtain precise photometry and recording the changes in the stellar brightness as function of time. And as you can see here, when this is a purely geometrical phenomena, so when we have a planet which crosses the stellar disk with respect to the observer, and we are aligned in the same line of sight, basically we can record this characteristic dimming of the brightness. And from the specific shape of the signal, we can, of course, get the period, and we can get also the radius of the planet and its inclination. That's because the more larger in relative units with respect to the stellar disk is the planet, the deeper the transit will be, and of course it really matters at what inclination actually will transit. This is very, very briefly, yeah. But with the transit method alone, we cannot get easily eccentricity and argument of periapsis and also the mass. So we need usually radial velocities or TTVs. This is the transit timing variations, which I'll define a little later. But the idea here is that we can actually detect multi-planets just as the radial velocity method, and it's actually not too complicated either. So what you have observed is basically the contribution from the two transiting planets. So this is planet 1, and then we have planet 2 over here. So the concept is not too complicated, just to understand how we detect exoplanets. And of course, the best possible way is if we have synergies between radial velocities and the transit method. So that means that we can detect the planet and characterize the planet with both of the methods. So this is one example. This is GJ486. This is a Carmenes survey target, which we publish in Science. And this is one of the closest exoplanets, which we could actually measure its bulk density. So basically, this was a Carmenes survey star. We detect the planet in the radial velocities, which are actually complemented with the maroon X radial velocities. And we waited a little bit to see what will happen with the TESS survey. So in the TESS survey showed that actually the planet transits. Usually it's the other way around. TESS discovers the planets first, and we tell us, okay, we have to observe with radial velocities this particular star to get the mass, but in this case we detected first on the radial velocities, and then it turned out that it's transiting. So when we combine the two methods, well, one can characterize good the radius, and the other can get the mass, and the transit method also gives you the inclination, so therefore we can get dynamical mass, okay, of the planet, and also the planet radius. And when we have the mass and the radius, we can get what? The bulk density, okay? So it's a great for estimating the true mass and the bulk density of these exoplanets. And that's of course not only for these planets. In general cases, if we combine radial velocities and transits, we can get the true dynamical masses which allow us to determine whether the planet is rocky, icy, Neptune-like, or gas giant. Okay. The problem, however, in this kind of low mass planet, so this was a very low mass planet, so it's about the Earth size, a rocky planet. I think the mass is about 3 Earth masses and about a little bit larger radius than Earth. Is that, as you can see here, still the radio velocity signal is pretty weak. Okay, so it's about a few meters per second, not too bad, but we cannot actually estimate the eccentricity. And this is a very important parameter. So it's more consistent with 0, but this is not only problem of the data, just basically because the orbital period is so short, it's about 1.46 days, then the interactions with the star, tidal interactions with the star take over and tend to circularize the eccentricity of the orbital eccentricity of the planet. Therefore, important piece of information is already more or less lost, yeah, because now we have the book density. Okay, we have the radius, we have a lot of parameters, but the eccentricity has been already gone. Okay, this is the problem also with the hot Jupiters. Yeah, that's why most of the hot Jupiters are nearly circular orbits, and we don't know with what kind of eccentricity they came into this orbit. So, what are the best targets to find the eccentricity? I think. If you look at the exoplanet demographics, this is a plot on your left side. Is the famous planet mass. Keep in mind this is planet mass plus minimum mass of the planet versus the semi-major axis, and on the right is the eccentricity distribution of the transit and Doppler method versus the period. And we can see immediately, as we've been discussed many times in this kind of exoplanet talks, that we have a well-defined well-understood bias towards more massive planets because we are just more likely to detect such planets. They're just easier to be detected. Of course, there is a bulk of planets which have Earth-like to about Neptune-size masses, which we found in many chains, chains of orbital multiplanetary systems. But of course, as I mentioned, these are typically closer to their stars, so therefore the inclination is close to 0. And what I think it's best to constrain the planet migration theories is actually to work with more massive planets, Jupiter mass planets, in multiple planetary systems with pronounced eccentricity. So here we can see here that in the right plot we have many exoplanets which have a very large eccentricity, which tell us something about the formation history. Now, keep in mind that I said that it's very difficult to detect eccentricity with the transit method, which is the blue, but keep in mind that many of these actually have joint observations with radio velocities and transits. For instance, they've been detected with the transit, but they have been constrained the eccentricity with the radio velocity method. So the radio velocity method is still extremely valuable in this case. So the multiplanetary system is a Rosetta Stone. So in these plots I show the stellar mass versus the same major axis and the eccentricity for all multiplanetary systems which have been detected, which have planet pairs larger than 1 Jupiter mass. So basically these are all multiplanetary systems composed of Jovian mass planets. And the dashed blue line here, it's the so-called ice line. So we know the planets must have formed much further out over here, and they must have migrated together with probably in pairs. And we know that actually planets migrate. So the question is, okay, how actually they migrated, and can we actually reconstruct these configurations giving their actual positions now? Okay, especially those which are trapped in the mean motion resonances, and they preserve a memory for the migration process. I will show how that works, that includes also the migration rate and also some other observables like the libration amplitudes of eccentricities, same major axis, and just the dynamical architecture of the system, more or less. And here we have many systems. You can see that we can actually measure very well the eccentricity, and eccentricity is very important if we want to trace the mean motion resonance. So speaking about the mean motion resonances, many planets actually reside in this so-called mean motion resonance commerciabilities, such as 2 to 1, 3 to 1, fewer to higher order resonances like 5 to 1, 6 to 1. They seem to not be clustered in some kind of a deterministic period ratios. So we can ask our questions, how many of these systems actually are locked in mean motion resonance? And I will show that even though these are the orbital parameters, the period ratios discussed in the literature, they might be actually different from the mean oscillating periods of these multiplanetary systems. And the idea is like, what can we learn from these massive multiplanetary systems, okay? So how they actually enter into this regime of being close to mean motion commerciability. So just a practical example, just to understand where the problem is. So I'll try to lead you through the cascade of the whole research here. So from taking the data to modeling the data to understanding the resonances all the way to the constraining the disk properties. So just let's warm up. So this is a practical example, very famous system, GJ876. It's consistent with 2 Jovian planets around a red dwarf. Okay, this was one of the Rosetta Stone systems which led to a lot of advancement in the planet formation theories. Basically, that planets might actually do type 2 convergent migration into closer orbits, being locked in a mean motion resonance. So here you can see the periods are close to 2 to 1, and these are obviously 2 Jovian mass planets. So I think this is about a Jovian mass, this is about 2.8 Jovian mass planets. So everything is pretty good, right? So you can see that the orbits are pretty well defined. So this is one of the first radio velocity observations for this star. And you can immediately model the orbits pretty good. So what we do usually is like when we find interesting system, we keep observing it over the years. Okay, so let's see what happens when we take more observations. Okay, something happened. Yeah. So we took more data and everything failed. Can anybody tell me what's going on? Why is that? Why these models actually are not holding? Yes? That's right, there are 2 more planets, but they do not account for this huge RMS in the residuals that you see. Okay, there are 2 more planets, but they are low mass planets indeed, but they only account to about a few meters per second in the signal. While here we are seeing hundreds of meters per second deviation from the model. Now one can say, okay, of course, Trifon, you can refit the model and it will match. Okay, you can do that, but I'm telling you, that will not help. So the reason why it doesn't fit is because this model over here is simply Keplerian model, which does not take into account the gravitational interactions of the planet. So if you try to build up to this model and take more data, it will fail. So you need to use self-consistent n-body model to constrain the data. And when you do that, and what we do in Landestein, what we develop this kind of tools like the ExoStriker, as it was already mentioned, and you fit, I'm not sure if you can see, but here it is a Keplerian and n-body model. So when you do n-body model, so we have all the planets included, including planet 4, which is hidden here. Then the model actually fits pretty well. And now we can move on. Okay, so this system is well understood. It's a highly interactive 2-to-1 mean motion resonance system, but the same happens for the dynamical signature of the transit data, right? So when we have these so-called transit timing variations. So this is an example of Kepler 88b, also classical example. So if you have only 1 planet and a star, you would know precisely when the planet should transit, okay? So this is a 2-body system. You can take a piece of paper and write it down, the Keplerian equations, and you can predict when actually that will happen. Now, if you put another body in the system, it's already, it cannot be solved analytically. You have to solve it numerically with n-body models. So the deviation of the transits actually are pretty large of this system, right? And you can see here they are like 500 meters, 600 meters, that's like 10 hours, same amplitude. Okay, so this is Kepler data, continuous duration of 3 years, and you can see here that they are, sometimes the transits are coming faster, sometimes are coming later. So basically there is something that disturbs the orbit of Kepler 88b. Okay, so this is not transiting system, but given the amplitude of the TTVs, we can actually get the mass and the eccentricity to some degree. So you have to apply this kind of n-body models in order to get the parameters. That's the bottom line. Just a short story. Okay, so you take data, whether it's transit or radio velocities, but if you try to fit it later on, it will fail unless you use the correct n-body model, then everything will come to its place. Now, why is this important? Because you know, scientists try to fine-tune their planet formation theories based on the distribution of exoplanets on multiplanetary systems, for instance, that circulate in the literature. But many of these systems actually have been published with Keplerian orbits. Okay, so they are valid only for a given epoch and under the condition that the planets do not interact gravitationally. So my point here, it's like I just want to convey the message that not only we should follow up these planets, but we should also follow it with the proper models, okay, and more data, which is certainly available in the archives. So, not really in the context of the talk, but I just want to show one more planet system which was published last year in Nature, for which we worked long ago. So this is a binary system with planets. So this is the new Octantis system. And here in this case, first you see the radial velocity contribution from the star. So we have a subgiant star, and then we have what we find out is to be a white dwarf. With about 60% of the mass of the star, and on the residues we see the planet, and the planet has very challenging orbit. It can only be stable if it's in a retrograde orbit, so meaning that the planet orbits in this direction, then the star orbits in the other, and then we can have a stable solution. But you cannot actually apply even Keplerian models here, because actually, you can apply Keplerian models, but they will not be valid, because then you have to do the n-body stuff. You need to find out the mutual inclination between the bodies in order to make sense of the data. Okay, so that's why the n-body models are essential not only for multiplanetary systems, but in some challenging systems, just like the binary star systems, like New Octantis. And we speculate that this might be a possible second-generation exoplanet, because in this challenging orbit, it could, in principle, be formed, either being captured, or maybe because this is a white dwarf, maybe it evolved, it ejected a lot of mass as a giant, as an asymptotic giant branch, which was condensed on a retrograde orbit around the primary, which was a secondary before. Okay, so before this was a primary, it ejected a lot of mass, it condensed over here, and now we have a primary, which was secondary before. Okay, this is just to mention this system, because I think it's relevant in terms of the modeling. And let's again talk a little bit about GG876. This is one classical example, and this is one of the systems that I love to work with, and I think it has a lot of potential yet. So some of these data have been accumulated over the past couple of years, also with Spirou, Carmenes. So there's a lot of radial velocity data for this star. And what we see over here, this signal over here, it's not because of the planets, okay? This is the precession that we observe. So if you can see here the time scales of the precession of the two orbits, orbiting in 2-to-1 mid-motion resonance. So one makes two orbits, the other makes one. But they're always in aligned configuration, and they librate and precess. We can, within one typical time scale of maybe a PhD plus a postdoc, or two postdocs, we can actually measure the whole precession rate of the system. So this is amazing. And if you take the dynamical model parameters and you integrate them forward, what you will measure, it's also the typical period ratio and also some other parameters like the delta omega. This is the secular apsidal resonance angle. You see that actually librates around 0. I hope you can see. But there are also two other variables called the theta 1 and theta 2. These are the so-called resonance angles. And these are very important, right? So the fact that it's actually orbiting, the orbital period ratio is close to 2 to 1, it doesn't mean the system is in resonance. It has to observe these so-called resonance angles in order to get a feeling whether the system is indeed synchronized or not. Okay, so this is the only slide which I have some little math for the students, just to define the resonance angles. So if we have resonant angles of n over m, so mid-motion resonance, so basically the resonance order, it's q, it's n minus m. So for example, if we have like a 2 to 1, 2 minus 1, this is resonance order of 1, first order resonance, okay? And then the resonance angles are actually defined with this formula over here, and everything that we have, that we need to know, it's only the mean longitude and longitude of periastron, and these are variables that we can actually measure constrain with the dynamical models, and then integrate forward with n-body models, and we can actually check whether the libration angles oscillate or not. Okay, I think that's pretty easy. So for the 2-to-1 mean-motion resonance, basically, first order resonance, we have two resonance angles, which I showed in the GJ876. We have two resonance angles, theta 1, theta 2. For 3-to-1 mean-motion resonance, it's a bit weaker resonance. Then we have three resonance angles, and for 5-to-1 we have 5, for 6-to-1 we have 6, and etc. So basically, and additionally, one important variable is the delta omega, which is the difference of the periapsis. So this is also important to see whether the system is in aligned configuration. Okay, so this is just a small recap, just to understand what the resonance angles are. So these are just variables that we can measure if they oscillate. Okay, another example is the TTV system. This is interesting because if you look at the period ratio, okay, so this is the radial velocities from the LIC data, and we have some from CRIRES. So this is what we published in 2014, part of my PhD thesis with Andreas and Sabine. We have period of 740 days and 400-day period, so that's very far from 2-to-1, right? Oh, how can you say this is in resonance? Well, you integrate orbits, you integrate the dynamical fit, and what you can see is that the period ratio actually oscillates with a very large amplitude, but the mean is 2. Okay? Same for the eccentricity, so within observable time frames, let's say this is 50 years, so within 10 years or so, the eccentricity will change dramatically, so is the period ratio. So if you observe this system, I don't know, in 10, 15 years, the period ratio will be different. And theta 1 and theta 2 librate, so is also the, delta omega. And yeah, the system shows very strong oscillations and same major axis and eccentricity, and is locked in an anti-aligned mean-motion resonance. So basically, delta omega librates around 180 degrees rather than 0. So if you take this plot, which I showed you earlier, and if you take the best fit parameters, okay, which circulate in the literature for a given epoch, you will find out this system is outside of this so-called 2-to-1 commerciability. So it's a valid question, how many of these systems actually are close to 2-to-1 if you integrate them with the proper models and the n-body analysis? It might be a sufficient fraction of those. I mean, I'm trying to put hand on most of those, but it's quite a lot of work, to be frank. So some of these might actually lie in the resonance, although it's not really obvious. So another source of great Jovian mass pairs is actually test data. I was one of the skeptics in the beginning. When the test was launched, I said like, oh, okay, to find Jovian mass planets and to characterize them, you need basically to have TTVs, but the test sector it's not going to allow us because one test sector is about 27 days. So how many multiplanetary systems we detect in one sector? Of course, we didn't know in the beginning that tests actually will be extended several times already. And one of the important areas where we can look for this multiplanetary system is this so-called the continuous viewing zone of tests. So many text sectors actually intersect over there. I just want to emphasize also the WINE survey for one Jupiter exoplanet, which was extremely profitable in this sense, because as you can see here, even if we detect one planet, if we have multi-sector data, we can detect many of these so-called warm Jupiter planets. And most of these actually come on pairs or even more planets involved. And the TTVs, the so-called transit timing variations, actually multiply if you move further out from the planet, from the star. Okay, so Jovian mass planets will have a very large amplitudes and therefore will be very easy to characterize. And also, because it's tests, we try to find out more time to observe it, of course, to validate these planets with radial velocities, and this is a strong synergy between TTVs and radial velocities from this survey. So this is just a small recap of the important WINE TTV systems up to April 2026. We have at least 10 multiplanetary systems which we actively work. One was actually just accepted in Nature, which is you will hear about that soon. And there are really gems here in terms of multiplanetary systems. So we can see here the period ratios are mostly between 2-to-1, 3-to-1. There are some other odd numbers, but basically we see many Saturn, Jupiter, Saturn, Neptune, Saturn, basically massive planets which interact strongly. Not everything is in resonance, yes, okay, most of the planets are actually not in resonance, which is okay, but there are some which are clearly, undoubtedly in mid-motion resonance. So this is one example. If you take the two supermassive Jovian mass planets, part of this survey, there is only one transit, by the way. There is only one monotransit, but we hit this system with radial velocities, and we were able to constrain the planets with radial velocities. And because they are so massive and they induce such a strong signal, we find out that they are more consistent with the 6 Jupiter masses and 8 Jupiter masses with periods of 77 to 155 days. Strongly interacting system, one of the most densest planets pairs that we have found, and is purely perfectly in 2-to-1 mid-motion resonance. Okay. So, few other. I think I should definitely mention the TOI 4504. So this is the system that we discovered with the largest TTV amplitude ever discovered. So as you see, the TTVs, typically when we talk about TTVs, it's about minutes, hours, but this one has the same amplitude of 2 days. Okay, so end-to-end amplitude is about 4 days. So you can imagine the swing. Only one planet was transiting. Only one planet was transiting when we published this signal. And there's an additional warm super Earth in the system. But recently, and we've been also working in a follow-up paper, it turned out that as predicted, TOI 4504D, which was the unseen perturber, will start transiting. So this is a very nice plot from Almenara et al. So you can see here the plane, actually, the orbital plane. This is the super Earth over here. Well, we don't know actually the mass. It probably is a mini Neptune. But the two Jovian mass planets actually are librating with a very large amplitudes. And you can see they're also precessing just like GG876. And while planet C was transiting and we detect the TTVs there, planet D start entering in the stellar disk. And here, maybe if you can see, so this is the transits of planet C, and here we start seeing already, as predicted, that the planet will start transiting. This is the unknown perturber. So we're talking about 3 point something Jupiter mass planets. There's another interesting system that I've been working together with our wine collaborators, which basically started as a collaboration between Max Planck and some of the Chilean institutions there. We have a very, very productive collaboration there. We're working with too many systems, and it's not even possible to model everything that we got. So last year we got 3 transiting warm Jupiters, which are close to 4-to-2-to-1 in motion resonance. This is so-called Laplace resonance. Okay. They're not exactly in resonance, so I'm showing here just the TTVs, not transits, but we also have radial velocities from Espresso, Harps, Ferus. It's not in resonance, but what is very important is that we observe this so-called apsidal alignment of planets C and D, so basically which actually induces these TTVs in a more enhanced way. So, but you can see the period ratios are not really now. They could have been in Laplace resonance before being get out from this resonance thanks to some overstability, for instance, in that sense. Okay, and just to understand how that works actually, why these are important. So just let's take one system for which we know that is in very deep resonance. This is the new Fuji brown dwarf system. It was published by Andreas Kurenbach and collaborators a few years back. So we only rely here on the radial velocity data, but this radial velocity data, which I don't show here for simplicity, we apply dynamical models, and we are very confident that the system is in a deep 6-to-1 mid-motion resonance, which is very rare. So this is a very weak resonance, right? So just to assemble this resonance is already a miracle. So why is that important? Because we have these 6 resonance angles, okay, librating around 0. These are the anchor points for us. So how to recover this resonance? We can do some reverse engineering. So we try to form this system with n-body integrations. Now, we took some classical numerical setup for this force migration terms. For example, we take the Simba n-body integrator, and we add additional physics, like let's say the migration rate or different geometries. So basically we try to find out in what conditions, in what migration rate, and what eccentricity damping we see the planets actually will converge into this 6:1 period commerciability and be trapped in this resonance, okay? Because this is a probabilistic phenomena. It might or might not locked in a resonance. For example, 6:1 is pretty small chance to get it to there. So you need to have special conditions. And on top of that, so we do this kind of simulations. For example, we start the planets and we evolve them numerically, but we drag the planets into closer commerciabilities. So at some point when they locked in the 6:1, we will see, for example, liberation of the eccentricities, whether delta omega will liberate, and also while it's outside of the resonance, at some point we start converging into resonance. And our idea here is to have something like a quasi-local function, which our observables will be, let's say, the amplitudes of theta. Okay, so they are amplitudes of eccentricities, period ratio, and etc., etc. And we draw nested sampling parameters, nested sampling analysis. So basically, we take the orbital configurations, and from the posterior analysis of our radial velocity analysis, we integrate them forward, okay, and we try different configurations which will converge to exactly the configuration that we observe with the radial velocities. And therefore, we can constrain, let's say, the initial eccentricities, the initial geometries, and the, let's say, the migration rate, which in this case should be about 1 AU per 1 million years. If you take this A dot over A, so basically it's 10 to the minus 5 or something like this. So I think it's pretty, it's faster than exactly. So it's about 1 million year, I think, for 1 AU, the planet to migrate. Okay, so I hope I didn't miss anything. I think one slide is missing, but nevertheless, I probably it's time to close anyway. Why the Jovian massive multi-planet systems are important? Okay, so massive multi-planet systems with enhanced eccentricities are sensitive tracers for strong planet-planet interactions. Okay, you need to get the eccentricity, you need to constrain it, and therefore because the eccentricity is a fossil record of earlier events that happen in that system. For example, whether there was a planet-planet scattering or migration. Convergent migration processes, and it can actually allow you to determine what happened. So radial velocity and TTVs, of course, are important data for constraining the dynamical masses, eccentricities, and long-term stability. That's great. So that's why Jovian mass planets will have larger signals, and therefore we can get better constraints on the parameters. Of course, I mentioned the proper n-body modeling. This is important in order to get the resonant systems from near resonant to secular interacting architectures. And resonance angles, subsidal libration, all kind of oscillations and amplitudes of eccentricities and period ratios are also anchor points for the n-body analysis. So we need to try to converge to the system that we observe in the semi-amplitudes of these parameters, like the resonance angles, by doing a smooth migration capture simulations. And that can tell us, for example, what should have been the disk lifetimes, and what will be the viscosity of the disk in terms of migration rate, for instance. Okay, so these systems are Rosetta stones for planet formation because they link the observed architecture with physical processes. Just to emphasize that here in the Landesteinwarte, we are actually doing the whole spectrum of analysis. So we plan, build, and operate high-precision radial velocity instruments. We conduct the surveys, including the TESS follow-up surveys, mostly joined also with the Max Planck Institute and the Chilean institutions. We identify massive multiplanetary systems, and we derive physically consistent n-body models and derive posterior distribution from them, which we test for long-term stability, and then we try to reverse engineering construct via more dedicated n-body stability analysis. And basically, that's it. What I wanted to convey the message. I hope I convince you that getting dynamical analysis of massive multiplanetary systems is important, because it can really help you to constrain some formation paths of the exoplanets in general. And that's basically from me. Thank you very much. I think it was on time, more or less, yeah?
Perfectly on time.
Good, okay.
I will open the floor to questions, especially students and postdocs. And I'll allow some awkward silence. You're not a student or postdoc.
Well, for example, when you have, it doesn't need to be. For instance, if you have only radial velocity observations, you don't know the inclination. But for example, for systems like GJ876, in principle, you can actually constrain the mutual inclinations, because the n-body model allows also for inclination and line of note to be parameters in the fit. Because the dynamical model will be different if they're, yeah. So that's actually go in. I mean, maybe I simplified a little bit because I didn't want to go too far. But for the radial velocity systems, just like GJ876, you can do that. For some, it makes no sense because it's poorly constrained. But when we have TTVs or photodynamical modeling with radial velocities, so basically we know the inclination from transits, we always fit also the inclination. Oh, sorry if I skip it, but inclination is a parameter, yes, and it's particularly the mutual inclination is very important. Well, I think here, right? Here, actually, this model. Well, it's not my paper. It's not something I did, but it's actually the same thing. You can see that the models actually assume different inclination for function of time. Therefore, the planet will start transiting over time. So the inclination is a parameter. So is in the n-body analysis.
More questions? No students today? So many students in the end.
Hi, thank you for the talk. You showed that the binary systems are also affected from the planet formation process, and we can also check the effects of the planets on the binary formation or binary evolution. But when it comes to the Jovian planets, I guess that because of the mass, the evolution is even more affected. So first, is it possible for such systems to form Jovian planets in vicinity of binaries? Because I know that
this is a Jovian mass planet. It's like 2.1 Jovian mass planet. Wow. It definitely will be difficult, yeah, because of the gravitational perturbations. I mean, that will immediately eject any disk that you can form planets. But that's why we believe that this planet, it's not first generation, it's probably a second generation if it is formed in this channel. I mean, here, obviously, you cannot have a protoplanetary disk in this configuration. But most of the stars in our galaxy are part of binaries, and we found many planets in binaries, but they're much further out. But the moment you start getting closer and closer and closer, so close separations to about 20 AU, there's a limit there where the planet formation will become very inefficient because of these perturbations from the secondary. So whether they can form Jovian mass planets, we know many. Not many, but we know a sufficient number of binaries, close binaries with planets. So we try to understand how these processes actually happen and how planets have been formed. But generally speaking, if you just take an n-body simulation and you try to simulate the planet formation in this kind of binaries, you hit a rock, actually.
And an additional question is, which is a little more general, but what should be the signatures that we should look in such binary systems that would show the existence of an additional body like a planet?
Well, speaking about data, for instance, well, many binaries have been actually overlooked because they said, okay, they took several radial velocities. It's becoming clear that it was very clear that this is a binary, and they've been thrown away from the surveys because of these considerations. Yeah, you cannot form planets in a closed binary systems, for instance. But what we are actually planning to do, and we are actually trying to find out, is like, okay, if we take a survey of binary stars, for which we know this kind of large radio velocity excursions, whether we will find some signal like this hidden in the residuals from the binary. That could be the first sign. And of course, from transits, you might get, circumbinary planets. I mean, that's clear. But here, different type of planets, right? So these are S-type planets, this so-called satellite type. So you have star, circumprimary planet, and then you have another perturber. These are more difficult, and this can be traced back with radio velocities, but you need a dedicated survey for that. So you model the binary, and whatever it's left possibly could be a planet.
Is there a model for why in this case you can even get into a mean motion resonance when you have a counter-rotating?
Okay, first let's show. There is no low order resonance in this case. Okay? But there will be a paper soon which actually claims, and I'm part of this paper, dynamical paper, which claims that actually there is a very high order retrograde resonance. It's something like 28 to 11 or something like that. Yeah. So it's crazy. It's crazy, but if you spell out all the resonance angles, you make all the math, you find out that there is something there.
But that could just be coincidence then, in principle.
Could be coincidence, yes. You can always find some period ratios. I mean, we discussed that in a way. So, yeah. If you take, I don't know, asteroid, you can find it in a period ratio with 30 to 1 with Jupiter, for instance, or something like this. Doesn't mean that it's in resonance, right? So you need to check. So for this system, actually, what stabilizes, and we found it is actually the periastron advance of the planet with respect to the binary. So basically, they in the retrograde case, it's a little more complicated. I'm not sure I can write it down here, but because it's in the retrograde case, it's with a minus. So basically, one planet exceeds from here and the other from the opposite. And if you take delta omega, actually, we vibrates around a constant angle, and this is the stabilizing mechanism here. But how planet actually formed there, we shall see. Gonna be difficult to get in a retrograde orbit.
Trifon, I have a basic question concerning the modelization. When you showed, we're talking about the migration.
Okay.
You said, or my question is, the migration you put in, so to say, by hand. You change the angular momentum of the orbit of the migrating planet, I guess, by hand.
Yeah, so this is like a forced migration term. So you're kicking the system, the planet with every step.
But perhaps not hard enough, or not too hard, since otherwise
it's not hard, no.
It should have the chance to get caught in a resonance, right?
Yes, so this is done with Simba, and the Simba it's symplectic integrator. So basically, the time step is adjustable automatically. Yeah. So basically, when you do that, you have a couple of force terms. So in this, just in details, in this, these are part of the code called Simba kick. So you apply before you apply the Keplerian part, there is a kick. So if you do it carefully without destroying, the energy of the system, you can actually simulate like a interaction with the disk, basically, like friction with the disk. So actually, you're pushing the system a little bit closer and closer and closer.
But you have to be a bit careful.
Yes. Yeah, okay. I fully agree with that. I mean, this is well-established methods, but of course, the most appropriate way is to do it in a hydrodynamical simulations, for instance. I'm not an expert in that. I mean, I hope people can take these systems that we analyze and publish, and they can do the more detailed work. So this is a proxy for the, for the planet formation.
So you talked a lot about planet formation. I mean, I think there are even more, but different scenarios.
So Yeah, I guess you can do that. Yes, I mean for the second question, I guess you can apply some kind of stability considerations in planets that cannot reside, but it's very difficult. I mean, nature keep amuses us with some very complex configurations. So I'm very hesitant to do that. But of course, there are some limits. For example, when the system is very eccentric, let's say, obviously there is a you can actually estimate what the stability region would be. Yeah, and unless I don't know, there is some kind of very weird resonance with some other body, like one-to-one resonance or something, you know, then one can say, okay, there are limits. I mean, you have an eccentric planet, and that planet actually goes to orbital separation of x and y, and because of the Hugh sphere of influence, it different parts of the orbit is different, you can actually eliminate all these possibilities. I mean, you can do that even analytically, I think. Or you can do some test particle analysis and check which systems can actually survive and which not. You can do that, yes. And about the planet scattering possibility, there is one system that we published a couple of years ago in Carmenes. It's GJ1148. It composed of two Saturn mass planets, one of my favorites, yes, around an M dwarf. Interesting system, and both of these planets are very eccentric. One resides in the habitable zone of about 40 days, the other is 530 days. So they don't interact dynamically much. So applying a dynamical model, it's not super important there, because they're further apart. But they are both in eccentric orbits and aligned. And there was a paper published last year, which were able to reproduce this system with planet scattering. So if there was a third planet in the system, and you just inject the planet in different different geometries, different positions, eventually you might end up in a system that is similar to what we observed in 1148. So this could be one channel to form this kind of Saturn mass planets in eccentric orbits. But of course, it could be also migration. I mean, interactions with the disk excite the eccentricity, and that's it. So you can always, with an n-body simulations, you can get almost everything you want. if you sample enough, you know. So I don't know. It's a great paper, but it proves that it's possible to form with planet-planet scattering. Whether that's the dominant channel of these eccentric resonance systems or near resonant, I can't really tell you at this point. But you can try to reverse engineer it. Just the permutations are too large to sample from.
All right, I see no further question. More question? Yes.
Hello. I was wondering a bit more about this resonance. So, first of all, how many of like multiple planet systems are in resonance, and what exactly like is it physically, and what is the conditions that what the reason why some multi-planet systems are in resonance or not in resonance?
Okay. So let's start with the statistics. I don't know how many systems in resonance. I cannot take it out from my pocket. I don't know. But the resonance systems, even looking at the Kepler, for example, transiting systems and also radial velocities, are rather rare phenomena. Most of the systems reside nearby resonance, okay, near to, let's say, 2-to-1 period commerciability, but not exactly, or 3-to-1 or something like this. So it is believed that they might have actually been in resonance in the past. So they, for example, they've been formed. I mean, I can talk to you, for example, let's say, from the perspective of massive planets, right? So they've been formed much further out when there was enough gas, solids, and ice, so to condense all these giant mass planets. And they start interacting with the disk, and they start migrating, and at some point they might have been locked in this 2-to-1 mid-motion resonance. But over time, when the disk dissipates, and if they are too close, for instance, then the tidal interactions with the star might actually take out the system outside of the resonance. But that happens over billions of years. It's not happened overnight. So what we believe for this piece in a pod planets, like we say that's like many multiplanetary systems composed of Earth mass or Neptune mass planets, like the TRAPPIST planets or even more massive. They might have actually come all together in chains of resonances. But over time, because of resonance overstability, they might have been off. Okay, there might have been even instabilities in the system. When one planet actually becomes unstable, they collide with each other and they destroy the resonances. So, but the idea it's like if you have multiplanetary systems and they migrate in a disk, there's a pretty good chance to be locked at least in the 2-to-1 resonance. Or the first order resonance, like 2-to-1, 3-to-2, 4-to-3. That's why we see this kind of commerciabilities in the small planets. But the problem there is that the eccentricity is not well defined. So therefore we have 0 omega and we cannot study the resonance angles. Yeah, so let's see. Here, right, so we need the mean longitude. And the mean longitude, we need also the omega. So when the eccentricity is 0, I mean, it's very difficult to get whether these systems actually vibrate in a resonance. Let me see whether I showed it. Okay. So I don't know how many exactly it's in resonance, but those massive planets, like what I showed you, they have a much higher chance to remain in resonance, okay, because of this strong interaction. So they are synchronized and they vibrate, they oscillate with a large amplitude, and when the disk dissipates, they remain when they are. Okay? If it's a large chains of many planets, small planets, it's more likely to disrupt the resonance at some point. So that's why I like the massive planets, because there is a good chance that some of these will actually remain in resonance for the lifetime of the universe, for instance.
So you don't simulate like this transition from resonance to non-resonance.
Okay, so I showed you here only when I capture resonance, but
Yeah.
many of these actually are escaping the resonance.
Okay.
Yeah, and I just discard them. So then the log likelihood, the quasi-log likelihood is in minus infinity, and I say, okay, this configuration is not likely, therefore I don't discuss it. Yeah, but majority of the samples actually, like I don't know, it's hard to say in this particular case, but majority of the configurations actually will skip the 6-to-1, and they will continue to 5-to-1 to 4-to-1. 5-to-1 has higher probability, 4-to-1 has even higher, 3-to-1 is very likely, 2-to-1 is almost certain capture. So, yeah, this is probabilistic, right? So I'm showing you only the good examples, but many of the samples actually pass like a knife in a butter, right? You just don't care about the resonance at all.
Okay, thank you.
Okay. Then, this time I don't see any more questions. So let's thank our speaker again.
Thank you.
And you can all find Trifon at